Hello, this is Babu Dan again with part 2 of mechanical ventilators. Okay, so let's begin this PowerPoint with the end in mind, which is to be able to use the LTV 950 ventilator as a precision oxygen air mixer in order to test various saturation levels for the wind power oxygen analyzer. We need to keep the peak flow rate within the wind power max flow rate. We need to be able to mix oxygen with the concentrator flows, which are limited to 1 liter per minute to 7 liters per minute. You will be selecting the respiration rate in breaths per minute and the tidal volume for the air-oxygen mix. You will be computing what is necessary for 30%, 40%, 50%, 60%, 70% fractional O2 ventilator output, and what concentrator flow rates are needed to achieve this. You're going to decide on whether to use volume or pressure control, assist control, or SIM-V control. And you also need to know how to disable triggered breaths. So just keep these things in mind as we go through the presentation. So ventilators have a confusing array of modes that make them seem like rocket science. Here are the basic modes. Pressure support, CPAP or BiPAP, simply increases the partial pressure into the lungs, which also helps open up the alveoli sacs and increase both the surface area and the partial pressure of oxygen into the lungs. The BiPAP is slightly different in that there are different pressures applied during inhalation and exhalation. The lower pressure during exhalation helps to offload carbon dioxide. Now we have assist control ventilation, volume control, which is pervasive, probably the most common mode used worldwide. And then we have assist control, pressure control. Now, assist control is used for very compromised, weak patients where the machine has to do most of the breathing. Synchronized intermittent mandatory ventilation, or SIM-V, gives the patient more control over their breathing. And this is used as a recovery mode to help the patient develop normal breathing again, enhance the strength of their intercostal muscles, and it also has a volume mode and a pressure mode. Pressure support ventilation, such as CPAP, the patient controls the respiratory rate, the tidal volume of air delivered with each breath, the ratio of inhale to exhale time, and virtually everything else. The ventilator only provides pressure support to expand the alveoli area in which oxygen diffusion takes place, increase O2 partial pressure, assist inhalation, compensate disease, and prevent sleep apnea. It's limited to use on patients who can mostly breathe on their own and is not suitable for severe trauma and disease. Now, an exception is the CPAP bubbler, which is ideal for neonatal ICU, where a slight O2 increase with oxygen air mix can drastically reduce infant mortality. Justinian Hospital in northern Haiti was able to cut their infant mortality in half just by using CPAP bubblers, for instance. So this diagram shows the basic elements of an infant CPAP bubbler. We have the air-oxygen mix from the wall, or you may need a compressor with an O2 tank and a mixing valve to moderate the amount of oxygen in the mix. It goes through a humidifier, which keeps the infant's lungs from drying out, through a nasal cannula into the infant's nostrils, and then the expiration tube goes into a simple, it could be a plastic water bottle, which has been used in some low resource countries, and the depth to which you put the tube in controls very finely the amount of pressure that is applied on the infant's lungs, which is quite small. So an adult CPAP is also relatively simple and requires either a compressor or a turbine and a pressure regulator to increase the pressure and airflow to the patient circuit or cannula. Now, in the infant CPAP, we call it a bubbler because it's actually the air bubbling through a liquid which applies the pressure. But just as in the infant case, we need a humidifier to keep the lungs from drying out. And oxygen gas is often mixed with pressurized air from the compressor in medical applications. It's not always available, for instance, for home applications in a CPAP. In that case, it requires a metered valve mixer. Preventative maintenance is usually about air filter replacement and cleaning. The compressor may require leaf spring valve adjustment or cleaning. Motors could fail on a fan, for instance, and most common failure modes, drastic failure modes, are motor compressor failures, rings, valves, motors, brushes. CPAP ventilators have limited use and can't help patients with trauma to the lungs or nervous systems, which prevents the use of lung muscles and diaphragms. The controls are very simple because basically the lungs are capable of inhaling and exhaling on their own. It's a very simple fan turbine control system where you have a fan generating the pressure, pressure sensor which provides a feedback to control the speed of the fan to deliver the required pressure. At the intake you have an air filter, and at the output you have a humidifier before it goes into a breathing tube and a breathing mask which is fastened over the nose and mouth of the patient. Very simple. So bilevel positive airway pressure, or BiPAP, is a variation of a CPAP machine. Whereas a CPAP increases the partial pressure of both oxygen and carbon dioxide during inhalation and exhalation, which improves the transfer of O2 into the blood by Henry's law. It also reduces the expelled CO2 by Henry's law. But lowering the pressure during exhalation could increase O2 absorption during inhalation without reducing CO2 emission. And it could also make inhalation easier. That's the concept behind a bilevel CPAP or BiPAP, but for a simple concept, it is not so simple to implement. And unlike a synchronous CPAP, it needs a trigger to control to synchronize inhale and exhale states. So a BiPAP is a hybrid between a full function feedback ventilator and open loop CPAP machines, and it lacks the popularity of either. We mention it as a transition from open loop CPAP control to closed loop breathing control of a full-fledged ventilator. So we'll describe the basic concept and application of assist control ventilation, known as ACV or AC. A set tidal volume is set to volume control, or a set pressure and inspiration time, if set to pressure control, is delivered at a minimum rate per minute. Additional ventilator breaths are given if triggered by the patient. The AC or ACV ventilator is breathing for the patient without any effort by the patient, so it's suitable for anesthesia or very weak or compromised patients. Assist control ventilation by volume control was at one time the world's most prevalent ventilator mode. That is changing, but all ventilator modes have three physical properties which are useful and easily recognized by respiratory therapists to understand which mode you're using. Those are pressure, volume, and flow, and those are different depending on whether or not you're in volume or pressure control mode. Now, in volume control mode, you see that the flow is basically ramped up and kept constant during the inspiration period, the beginning of the wave. And that causes the volume to ascend as a ramp. Now, the pressure is basically varying according to the compliance of the lung itself. So that will be different. You'll see in the violet area, the small purple circle, a negative pressure. That negative pressure indicates an inhalation by a patient. When that happens, the ventilator recognizes that the patient is trying to take an additional breath. So it looks for a negative pressure trigger, and then it will force an additional breath into the patient. So the patient, if they want an extra breath, they get an extra breath. However, the patient can be unconscious and the breaths will be delivered at a constant flow during inspiration at a regular interval that is set by the minimum respiration rate. So here we have the waveforms of the three physical properties of ventilation: pressure, volume, and flow, that are most critical in describing the difference between modes of operation. Now on the left we see volume control, and on the right we see pressure control. Now if there's some familiarity of these waveforms, it's because they do have parallels in electrical engineering. You can envision a lung as an inflatable balloon, which in pneumatics is very similar to a capacitor being charged by a current. So the volume of the balloon is analogous to the voltage of a capacitor. So if you look on the left, if you have a constant flow into that balloon, the volume will increase in a linear fashion. Just as if you have a constant current into a capacitor, the voltage across that capacitor will increase in a linear fashion. In contrast, if you look at the pressure-controlled mode, you see that the pressure is instantly increased and held steady. Well, what that means is if you have a collapsed lung, the greatest difference in pressure between the collapsed lung and the applied constant pressure from the ventilator occurs at the very beginning of inspiration. And that's when you should have a huge spike in flow, which is what we see. And then gradually the flow rate will diminish as the pressure inside the lungs reaches the same pressure as that applied by the ventilator. And as the flow decreases, because the volume is the integration of the flow, you will also see that the volume starts to taper off. The growth of the volume starts to taper off. So in volume control, the flow rate is kept flat. That is a controlled variable. In pressure control, the pressure is kept flat. Now, which is better of these two modes? In our case, where we want to use the LTV 950 for mixing air and oxygen flow to change the percentage of O2. Think about that and why. So let's discuss the advantages and disadvantages that come from the difference in those pressure, volume, and flow waveforms between volume control and pressure control. So volume control has the advantage that you get a guaranteed tidal volume, which produces a more stable minute volume. Now remember, minute volume, which is respiration rate times the tidal volume of each breath, that is the most important consideration. That's the target for the respiratory therapist, is to make sure that the patient is getting enough oxygen in a minute as opposed to each individual breath. So the minute volume also remains stable over a range of changing pulmonary characteristics in volume control because you're controlling the flow against any kind of changes in pulmonary characteristics. The initial flow rate, well actually it's a constant flow rate, is lower than when in pressure controlled modes. It avoids that big spike in flow that we saw came from pressure control. And that can cause a high resistance reaction in the airway. So the disadvantages of the mean airway pressure is lower with volume controlled ventilation. When we talk about airway pressure, remember it's the partial pressure of oxygen in the lungs that increases the flow of oxygen into the bloodstream. So you would like to have a very high pressure in the lungs to push oxygen into the bloodstream. And the recruitment, because the pressure is applied more slowly, may be poor. The recruitment, we talk about, the alveoli expanding. And so if there's a poor compliance of the lung, which is basically the resistance, or in electrical terminology, we would call it the conductance. In the presence of a leak, also the mean airway pressure may be unstable. And this last one, insufficient flow may give rise to patient ventilator dysynchrony. Basically, you don't want to set the flow too low, or the synchronization breaks down. So pressure advantages. You have increased mean airway pressure. Again, you getting a peaking of the partial pressure of oxygen more quickly. So in theory, you get more diffusion across those alveolar walls because of the higher oxygen partial pressure that comes from a higher pressure early on in the lungs. And in the same way, you got an increased duration of those alveolar, the sacs being recruited or expanded. It's protective against barotrauma. What that means is if you're trying to force a flow, what happens if there's some kind of blockage in the lungs? Well, if the ventilator is trying to force a flow, that can be more damaging than if all you're doing is applying a fixed pressure. So, and the working of the breathing, the patient comfort may also be improved with pressure. Now, I've talked to respiratory therapists that say, oh, pressure is the only thing they use now. I'm sure that is not a universal case, but I think there is a migration from traditional volume control to pressure control. So here are some of the pressure disadvantages, though. The tidal volume is variable and dependent on respiratory compliance. So you don't know how much tidal volume you're going to get. You're just going to apply a pressure, and what you get is what you get. The uncontrolled volume can also mean that if you have a highly compliant lungs, it overinflates. That's not a good thing. That's overdistension. And that initial high inspiratory flow rate that we talked about, that spike in flow rate, that can cause a pressure limit trigger. SIMV, synchronized intermittent mandatory ventilation. Breaths are given at a set minimal rate, but if the patient chooses to breathe faster, the ventilator does not assist them. That's a key difference with assist control, where assist control assists every breath, even if it's initiated by the patient. One advantage of SIMV is it allows patients to resume normal breathing on their own by exercising intercostal lung muscles. SIMV takes more work than AC ventilation, and so it's used only as the patient gets stronger and is not at risk. Like AC, SIMV can deliver set tidal volumes, volume control, or a set pressure and time, pressure control. And the differences between volume control and pressure control are the same for SIMV as we discussed for AC. So let's discuss the advantages of each mode. So in assist control ventilation, we reduce the work of breathing compared to spontaneous breathing because the ventilator takes charge of every breath. Now, the patient can't initiate a breath, but the machine still controls how they breathe. That's different than SimV, where a patient can have a normal breath in between, where the machine is not controlling it. AC volume ventilation guarantees delivery of a set tidal volume, which can keep the minute volume at target, and that's a major concern for respiratory therapists. Pressure control ventilation, however, limits the peak inspiratory pressures, which is also a very good thing. The pressure support ventilation, basically we're talking about CPAP. That's for patient support, patient comfort, improved ventilator interaction, but really only for patients who have recovered and are not machine dependent. And synchronized intermittent mandatory ventilation, SIMV. Think of that in electronics term as like having a blanking period where the patient is able to breathe on their own if they can, and the machine won't interfere, but if they don't, in that period, the machine will take over. But it has the advantage that the patient can return to normal breathing at their own rate, their own volume, their own characteristics for those voluntary breaths with less interference in the cardiovascular function. Okay, so here are the disadvantages of each mode. So for assist control ventilation, there's potentially adverse hemodynamic effects that may lead to inappropriate hyperventilation. For AC volume ventilation, it may lead to excessive inspiratory pressures. AC pressure control ventilation has potential for hyper or hypoventilation with lung resistance compliance changes. In other words, the lungs can overinflate, underinflate. It varies because there's no feedback in terms of volumes delivered to the lungs. So pressure support ventilation, it only has apnea alarm as a backup. And again, that's for when the patient basically has recovered and has very little need for a ventilator. It's not machine dependent. And the synchronized intermittent mandatory ventilation has increased work of breathing compared to AC, and that, of course, is what it's designed for, is for improving the condition of intercostal muscles and a return to normal breathing. But of course, that requires more work on the part of the patient. Assuming the patient is ready. So adaptive smart ventilators are the wave of the future. Modern X-ray controls input body part information, then they determine all the parameters that used to be the job of the radiologist. The new high-end ventilators take data on patient medical condition, continuously measure lung compliance and other respiratory indicators, and adapt to intelligent hybrid pressure volume control modes, what used to be the RT's job. In fact, I spoke with a younger RT that when I asked whether or not the machine was in pressure or volume mode, she wasn't even aware of what that meant because she'd been trained on these new intelligent machines. So the job for biomedical technicians only gets harder if something goes wrong with smart ventilators. Fortunately, they also have self-diagnostic and self-test modes, and even decide when they need preventative maintenance. Okay, ventilator settings. They can be a bit daunting to a biomedical technician when they first encounter a ventilator. First of all, you select a trigger mode, whether it's a AC or SIMV, volume or pressure, and then set the sensitivity for a patient-triggered breath, which is on an LTV 950, for instance, is 1 through 9. You also want to set the respiratory rate, which typically is 12 to 16 for a healthy individual. Tidal volume is the amount of volume per breath, and that is set by height and gender for an ideal weight. It's different depending on whether the patient is male, female, and what their height is. Then there's positive end expiratory pressure, which on the LTV 950, that's actually set with an exhaust valve, which is variable pressure. And that is the end pressure after the exhalation of a breath, which is usually kept somewhat positive. And it is similar to what a CPAP does. Then there's the flow rate, inspiratory time, and the fraction of inspired oxygen. Now, an LTV 1000 will allow you to set the oxygen. The fraction of inspired oxygen for a 950 we actually have to calculate, and that is set by adjusting the flow rate of oxygen into the oxygen inlet port of the ventilator. Okay, you've gotten a lot of information, and we're going to take a break to do a small group exercise. You'll see there are 8 pictures on the left, and these are for the same setting. These are pictures of different feedback that the LTV 950 is giving you, and then there are 12 questions on the right. And now I'll mention that each one of these pictures is the same mode, so it just flashes different readings, and I've captured those by camera, and that information is what you need to use to resolve the 12 questions. The instructor can freeze the video at this point and give you adequate time as a group to come up with the answers. Okay, I hope you enjoyed the exercise and your break. Now we'll move on to ventilator trigger. There are 2 ways for a patient to initiate a ventilator-delivered breath: pressure triggering or flow-by triggering. They may not both be available in all ventilators. When pressure triggering is used, a ventilator-delivered breath is initiated if the demand valve senses a negative airway pressure deflection generated by the patient trying to initiate a breath greater than the trigger sensitivity. We saw that in a previous diagram of pressure, where the pressure had a small negative dip that was circled in purple, and that was the trigger for a pressure triggering breath. When flow-by triggering is used, a continuous flow of gas through the ventilator circuit is monitored. The ventilator-delivered breath is initiated when the return flow is less than the delivered flow, a consequence of the patient's effort to initiate a breath. Now on the LTV 950, you will see the sensitivity setting. It is in liters per minute. I will let you figure out which one is indicated in that case. To refresh your memory, tidal volume is the amount of air delivered with each breath. Now, normal tidal volume is determined by patient height and gender for an ideal body weight. So body weight is not so much a determinant of lung size. The appropriate initial tidal volume setting depends on numerous factors, most notably the disease for which the patient requires mechanical ventilation. Now, minute volume, which is, again, what needs to be monitored, is the tidal volume times the breaths per minute, which is the amount of inhalation-exhalation volume over 1 minute. So a typical respiratory rate for most patients would start between 12 and 16 breaths per minute. But that can vary quite a bit depending on treatment. So for instance, low volume ventilation might involve very low tidal volumes. And to keep the minute volume large, they then have to have the respiration rate very high. So maybe even 30 breaths per minute. So respiration rate can be monitored by ECG patient monitors by detecting the changing skin impedance across the chest as it expands and contracts with breaths. So it just comes right from the ECG leads. Ventilators can measure the respiration rate by detecting pressure or flow cycles. And ventilators can set the respiration rate by deciding how much time to allow after exhale to force another inhale. And again, the target is the respiration rate times the tidal volume must meet the minimum minute volume. Positive end expiratory pressure, or PEEP, is a ventilator setting that leaves a slight amount of positive pressure at the end of an exhaled breath, rather than allowing the lungs to equal the outside air pressure. And what that does is it keeps the alveolar sacs from collapsing at the end of exhalation, and it's required for some therapeutic treatment of diseases. Not every ventilator has a PEEP setting on the control panel. The LTV 950, for instance, the PEEP can be set by rotating the exhalation exhaust PEEP valve on the patient's circuit. So PEEP is basically a CPAP function. So while CPAP cannot perform a ventilator function, ventilators can perform a CPAP function. Here's a waveform demonstrating PEEP. If there were not PEEP, the waveform would be coming all the way down to the x-axis, down to basically zero pressure. You see here the inspiratory time at the beginning when the ventilator is inflating the lungs, and then there's a hold period, and then the so-called elastic pressure as the lungs force the air out force the air out, and then it comes down to this minimum PEEP threshold and does not get all the way down to zero. Okay, so the flow rate setting, the peak flow rate is the maximum flow delivered by the ventilator during inspiration, set by the RT. So in pressure mode, we know that the flow peaks at the very beginning application of pressure, and this would limit just how high that could go. We also know during volume ventilation, the peak flow rate is basically level. The flow rate is level. So one of the concerns about volume ventilation is if that flow rate is too small, it can create lung malfunction. Okay, the inspiratory time to expiratory time relationship, or the inhale to exhale time ratio, is important, and normally it's about 1 to 2. So you take about twice as long to exhale as inhale. Now that varies with pediatric and neonatal applications and some other diseases, so it's not always that value. And so RTs can set ventilators. Many times the way in which you set the that ratio is indirect. For instance, on the LTV 950, you're allowed to set the inspiration time, and that in turn will determine the exhalation time based on mode of operation. So you won't necessarily be able to, you'll be able to read that value, but you won't necessarily be able to alter it directly. Okay, now wake up and pay attention on this one, because for our evaluation of the wind power oxygen concentrator analyzers, we need to use the LT 950 as a precision air oxygen mix function. And you can do that using the chart provided by CareFusion Pulmonetics. You see there are multiple lines here. Each one of the graph is for a different minute volume. And so you can see what minute volume is required to achieve an oxygen saturation. Now, the way in which they present oxygen saturation, FiO2, or fractional oxygen, you have to multiply that number by 100%. We go by percent, they go by just a decimal value from 0 to 1. But our oxygen concentrator, the max flow is 7 liters per minute, so that kind of constrains what we're able to do. So one of your questions I have for you, just looking at this chart, was the maximum VE to obtain 60% oxygen at 7 liters per minute O2. So take a minute and look at that. Okay, time for another small group exercise. Choosing the appropriate settings for the ventilator to produce the correct oxygen saturation for 30%, 40%, 50%, 60%, 70% O2 coming out of the ventilator, which we can then use to calibrate the wind power oxygen concentrator analyzers. You need to figure out how to set up this ventilator and what the settings are going to be, and use the chart on the left to determine flow rates and settings. Now, the LTV 1000, for instance, and many of the higher end ventilators, they actually allow you to set the oxygen concentration, which, they have an internal oxygen sensor and they control the mixing. You don't have to worry about, you don't have to use a lookup chart. And that would be great if we had that. We don't, so we have to vary the flow of oxygen into the oxygen inlet on the ventilator to achieve these different saturation levels. Okay, well, hopefully your instructor stopped the slideshow and gave you time to do the previous exercise. If not, he should back it up and stop it and complete that exercise, and then we'll move on to just a very short description of troubleshooting the vent, because our main function for this seminar is to get you familiar with how to set up a vent, how to use it, not be afraid of it, and the troubleshooting is a whole nother seminar because it's quite complicated. There's no way we're going to cover that in just a day. So, but some of the common problems that you would have with a ventilator as well as an oxygen concentrator, you're going to have leaking tubes or seals. Leaks are always the number one problem with any kind of pneumatic system. Clogged air filters is right up there. And faulty or uncalibrated oxygen sensor. Now, we mentioned, for instance, the LTV 1000 has its own oxygen sensor, and it can control the amount of oxygen saturation coming out of the ventilator. However, that oxygen sensor will age, and if it's a chemical sensor, which most of them are, it's going to age quickly with exposure to oxygen, and you will find that it's not, when you test the oxygen output, you'll find with your wind power, you'll find that it is not producing the oxygen concentration that it says. So that's one use, calibration use, for your wind power analyzer with a ventilator that has an oxygen saturation setting or control. Pressure sensors can be a problem. Flow sensors, we will cover those in a future seminar, hopefully. Faulty or mechanical electrical interlocks, again, form a plan, a hypothesis, and follow it. First of all, get the service manual, read it, read everything in it, and get as much information as you can about what it is you can and can't service. In the ventilator, it can be very limited. Remember, this is a class 3 device. It is a life support device, not like the class 2 devices you work on. For instance, an oxygen concentrator. If you mess with this and it malfunctions, a patient can die. Their life depends on it. So again, you really want to be careful about what you do and make sure you're working with a full database, knowing as much as you can. And a number one rule of medicine as well as biomedical is do no further damage, and make sure that you can back out any changes that you do. Okay, it's time to get our hands dirty and do some hands-on. The first thing I'd recommend is set up a ventilator with a patient circuit and a rubber balloon breathing bag so that you can see, set up the ventilator in normal operation, get over that fear of all the complicated settings, get familiar with doing those settings, and then when you're ready for the lab, you can replace that balloon with the wind power analyzer, and make sure that you connect the oxygen concentrator to the oxygen inlet, and then proceed with everything that's on this list. Your instructor should, have forms for you to fill out so that we can collect this data. We're going to use the data from these 8 analyzers that you have to identify by serial number to form a report for the donor, the kind donor who gave you these units. Part of our bargain is that we are going to provide them feedback on just how useful the wind power are, for instance, compared to the MaxTech UltraMax 02. So you want to make sure to evaluate that one too. The two reference wind power oxygen analyzers will be the ATC Lab Wind Power and the ATC Lab MaxTech.